Mechanical energy is the form of energy which can be measured for identifiable bodies. Chemical, electrical or thermal energy are not mechanical forms of energy since they depend on a great number of indistinguishable atoms or electrons. There are two forms of mechanical energy, kinetic energy and potential energy. One rigid body can have only kinetic energy. A system of two bodies, or a deformable body, like a spring or a basketball, can have both kinetic and potential energy.
Kinetic energy is the result of the mass and velocity of the body. Since velocity depends on the reference frame, so kinetic energy depends on the reference frame. Potential energy is the result of mass, distance between the bodies of the system and of the forces they mutually exert. Potential energy does not depend on the reference frame. It only depends on the state of the system itself. What happens when a body is falling from height, h? The weight of the body is a force. G is the gravitational acceleration, near the surface of the Earth. The work done, by its own weight, on the body, along the fall, is equal to the product mgh. This work is energy received by body A, with mass ma. That's why the kinetic energy of body A increases along the fall. Kinetic energy is the only form of energy that the one body A can possess. Please, solve this easy question. Find the velocity of body A when it hits the ground, after falling from a height of 50 meters. The value of g is approx. 9.8 meters per second. Find the work done by the weight of body A on A, itself. This work is energy received by body A which he accumulates as kinetic energy. Note that we can cancel the value of the mass of the falling body. That's why mass does not affect velocity, during the fall, as Galileo deduced. Energy was given to the body A by the system constituted by two bodies, the body A, itself, and the Earth. So, we have two systems. One system is body A, alone. The other system has two bodies, body A and the Earth. The system of two bodies, Earth and body A, stored potential energy. The system of one body, body A, stores kinetic energy. Let's think, now, about the system Earth plus body A. As the system is supposed to be isolated, its total mechanical energy does not change. We used the subscript I for initial, and subscript F for final. Initial, final, are the moments when our experiment or measure begins, ends. When the body is dropped from height h, it has zero kinetic energy and maximum potential energy. When the body hits the ground, it has zero potential energy and maximum kinetic energy. The blue ball is falling from different heights. You can observe the loss of potential energy and the gain of kinetic energy. Now, the ball is subjected to a higher gravity. So the potential energy of the system Earth plus ball is higher for the same height. In low gravity, the ball hits the ground with lower velocity because, for the same height, it did not receive the same amount of energy from the system of itself plus the Earth.
You can observe the change in velocity as the ball is falling or going up. When on top, the ball has zero kinetic energy. When it hits the ground, it has zero potential energy. As we know, the velocity of the body when it hits the ground is the square root of the product of 2, the gravitational acceleration, the height of the fall. If the ball rebounds to the same height, the velocity just after the collision is equal and opposed to the velocity just before the collision. If the ball cannot rebound to the same height, the velocity, just after the collision, is lesser than the velocity of the ball, just before the collision. It's easy to relate the velocity of the ball, when it hits the ground, with the height of the fall. The same relation is valid for the velocity at which the ball leaves the ground and the height reached by the rebound. One can compare the two velocities, before and after the rebound, just by measuring the maximum height before and after that same rebound. V after divided by V before the collision is the coefficient of restitution, E or CR. VA is the separation velocity, VB is the approaching velocity. The two terms are to be taken with the same algebraic signal, in order for the coefficient of restitution to be always positive. Please, solve the problem. Finding the coefficient of restitution does not require measuring the velocities involved. It's easier to measure the corresponding heights. After knowing the value of E, it's easy to find any maximum height before or after rebound, from the knowledge of just one maximum height. When there is total restitution of the velocity, E equals 1. When the ball becomes glued to the ground, E equals 0. How many times a ball will rebound before it has lost 95% of its mechanical energy? Coefficient of restitution equal to 0.7. Let's call to the coefficient of restitution, CR, in order to avoid confusion with the Euler's number, E. Multiply both terms of the fraction by mg. We have, now, the energies, after and before collision. The successive energies, between rebounds, form a geometric sequence with common ratio CR squared, and start value 100%, 100 and 1/100ths, that is, 1. As you know, the general form of such a sequence is, the nth term equals the first term multiplied by the common ratio, raised to the power of n-1. The n term refers to the height before the n rebound, as the term 1 refers to the height before the first rebound, the height from where the ball was dropped. So we look for the last term while energy was still higher than 5% of the original. The first term of the geometric sequence has the value 1, of course. Note that the exponent of CR is logarithm of 0.05. The value of n, 5.2, tell us that when the ball goes to its fifth rebound has still more than 5% of its initial energy. It has 5.8%. When the ball goes to its sixth rebound it has, only, 2.8% of its initial energy. Let's look what happens with higher values of the coefficient of restitution. Note the strong influence of the coefficient of restitution in the repeated loss of energy. The simulation confirms that, before the ball have lost 95% of its energy, it makes 5 rebounds. Note the dramatic increase of rebounds when the coefficient of restitution get a higher value.
There seems to be contradiction with the conservation of momentum. If E equals 1 and the velocity of the ball before collision with the ground is 2 meters per second, then the velocity of the ball after collision will be minus 2 meters per second. If the mass of the ball is m equals 5 kilograms, the change in momentum would be minus 20 kilograms meters per second.
But we are talking about the variation of momentum of the ball. We must not forget that the isolated system is constituted, not just by the ball, but by the ball and the Earth. After collision, the Earth moves along the positive direction, compensating the loss of momentum by the ball.
Let's do the math. We can choose, wisely, a reference frame where the Earth is not moving, before the collision. After collision, the Earth moves, even in the reference frame where it didn't move before collision. All velocities are defined in the reference frame of the Earth, before the collision. The velocity of the Earth before collision, in that reference frame, is obviously 0. The terms which include it do not show in the equations. Divide for ma in the two equations and for half in the second equation. Square the first equation. Note that its second member is binomial. Now we can subtract the second equation from the first, in order to get an equation with one of its members equal 0. As me, over, ma, multiplied by ve, appears in all the terms, we can divide the equation by them. Solve in order to the Earth. Recall the equation for the conservation of momentum and insert the value of VE on it. Divide the equation by ma and rearrange. As the mass of the Earth is very much bigger than the mass of the body, we omit ma.
Nothing wrong about the bouncing ball. Observe what happens when a small body collides with a body with much higher mass.
See you in the next video. The Ballistic Pendulum.